Good morning. Today we're going to see a very interesting topic, and that is what are the body plots in the frequency response. And for that purpose, I have set up this example that you have in here with two masses and spring dampers and a force in there, and the corresponding bond graph model in there. We have also set up the objectives. This as the output are the velocity of m sub 2 and the position of m sub 2 as the outputs. So in order to explain this, first we need to study the concept of what a transfer function is, the concept of what frequency response is, and with those two concepts we will study what the body plots are. Body plots are just a graphical representation of what we call frequency response. So let's go and develop this. So we have in here this say this objectives over here. This is your entire system, okay? So what I'm going to do is maybe I'll just go and perhaps a little dramatic here. We'll just select this, let's call it lasso select, to select everything that goes on in here like this. See this lasso in here? This is your system. Let's move it down a little bit. No, we're not gonna, but this is your system. We tried to select it, but it didn't select, so we're gonna go on with this. But let's just say whatever I selected, I am gonna say, okay, look, this is going to be my system here. And this is going to be in here. You're gonna have on one side, you're gonna have an input side, and then you're gonna have an output side. Okay, this is your system. Right? The system can have several representations. In fact, we can list them here, several representations that we can have for it. Since we have the ability to do these boxes, it's actually will look nicer here. If we draw a few options that we have to represent your system, and then we have maybe a third box that I want, and I'll do it down here. Okay. So in here you have several possibilities. One, so all this is your system, okay? System, system, system. One possibility is that you have in the time domain, you have, of course, your input. Input is a function of time, and the output is also a function of time. What do you have in here? You can have differential equations. Differential equations. You could have a state space. You could have a state space. This is ax plus bu. And you could have y is equal to cx plus du. And this is again your output in the time domain. And you have the input in the time domain. But you could also have a transfer function, like let's call it a transfer function. This one, however, the transfer function is in the frequency domain. This is the input in the S domain, and this one is the output in the S domain. So you could have something like this: S over S squared plus 2S plus 3, something like that. Okay? No matter what the input and the output of your system is, you can always make several tests. Test number one, say tests, you would say one is the step input or step response, meaning in the side of the input, I just put one function like this as my input, and I ask the system to find out, and this is my input over here. I could also ask for impulse response, or you could say test number two, and this could be a step response, or you could do impulse response. That is another test. And this is my input signal is going to look like a spike in here. I instantaneously put an input in here, and then I try to find out what the output is. So this is T, and this would be the input here. But I'm going to do test number 3. This is going to be a frequency response test. I'm going to call frequency response. Now, what does frequency response mean? It means that I take this using this transfer function, and on the side of the input, I'm going to change colors here so that on this side, I just put an input signal that is a, let's say, a sinusoidal function, yeah? But on the output over here, I have the same sinusoidal function, but maybe looks like this, a bit out of phase. So this is in here, I put my frequency input, like I have drawn it over here, on the side of the input and the output here. This is transfer function. And in here, I put different frequency, maybe this one. And my response is going to be also like that. So in this particular case, what I'm doing is I am putting an input. Let's just put it like a little, let's make like a table in here, where this is your input in the S domain, and this is be your output. And in here I say my input is let's say 1 hertz. And then the output in here response value A, let's say. You have 10 hertz, value B. I'm recording the response. 10 to the third, value C. 10 to the fourth, D. 10 to the fifth, E. 10 to the sixth, F. Now you see, what I'm doing here is I am changing the input frequency and seeing how the output is going to respond. But also, what I told you here is that I could have an input in here and the output might be out of phase. So in this particular case, we need to find a transfer function for this output, transfer function of the velocity of mass 2 is what we want. And also we need a transfer function of the position of m sub 2, which we also do not know. Okay? But first of all, I'm explaining to you what is entailed to actually build this response, the so-called frequency response. So what we have in here is that given this data, I can actually make a plot of the response of this. I'm going to say let's go farther down in here, and let's say so that we have plenty of space. And in here I'm going to make a plot like this. I'm going to plot on the horizontal axis the frequency in hertz, okay? And on the vertical axis, I am going to put the output, my output response. And in here I say, okay, look, this is going to be 1 hertz. And if you do here, it's going to be 10. This is going to be 1,000, so 10 to the third, 10 to the fourth, 10 to the fifth, and 10 to the sixth. Immediately you recognize that the scale that I have is logarithmic scale. Yeah? And this is going to be my output. Now, I am not going to predict the exact how the shape of that is going to be, but I'm going to give you just one possible answer in here. This thing could actually be like this, or maybe like that, yeah. And what I want you to see is that in the place where it goes flat, the input and the output are the same for this region that you see here, but not for these other ones. So you could have a situation where only on a certain region the response is a one-to-one correspondence between the input and the output. So what I'm trying to tell you is that this frequency response, this plot is what we call a body plot. But body plot has two parts. It has this frequency, but also, this frequency plot, but also has a second plot using the same scale, the frequency in hertz over here, and using this same thing, this in here. There. And again, I am just gonna make just one plot to indicate, and I'm not necessarily for this one, but it might look something like this. And what happens is this is the measure of the phase angle. You see, when you put the input over here, the output not necessarily can track the input perfectly. The output might be out of phase, although it's also a sinusoidal output because the input is sinusoidal, but may be out of phase. So the frequency response plot that we have has these two components. It has this one and it has this one. It has the magnitude and it has also the phase. So this is called the body plot. Is two parts. This is the magnitude plot uh, and the other one, this is called the phase, like this. Yeah. So I think it remains for us to do what we were going to do for this system. First of all, let's try to find these transfer functions, and then let's try to find these plots, these body plots. Okay, so what I would suggest that we do is the very first thing we do is to put this into the CAMG software, and we will do the simulation using the time domain, and we will use also the frequency domain. So why don't we go ahead and then we go into CAMG over here, and then we will put that in there. There we go here. So let's just look at this bone graft model over here, and then I think I have a, because I have the the numbers, I'm just gonna use the same thing to input this. I'm just gonna go a little farther out in here to make sure I have a space, and then I go into a one junction over here, and then I'm gonna go and click from here to here. Then I produce the click the I, and then of course the 0 over here. See, in the order that I'm entering this will keep the numbers exactly as I have them on my left hand side paper, as if I have it on paper, or in this case on this notes. And then we have the C element, which is over here like that, and then we have this one, yeah, which is for number 7, yeah, and then we have this one from here, and then the 0 from here to here, and then you have this 1 from here to here, and you have this R element, and then you have the C element. There we go. And I keep the same thing over here. This would be number 11, and then I have an SF element which is over here like this. Okay, so just to keep keep in perspective, I'm going to make a copy of this that I have on the screen and put it in my notes over there, right here. So I have my, where do we put the bone graft model? I guess we could do it right here because we are continuing the discussion here. So in here we could just write my output again. In this case would be the velocity of the mass 2, which is f sub 8, right? F sub 8 is velocity of m sub 2. And then the integral of f sub 8 would become the position of m2. So what I'm going to do is I'm just going to go ahead and obtain the transfer function for that, and then obtain both of those things that I'm looking for, both transfer functions in this. I'm just going to go to the interface and do MATLAB and allow these two programs to interface with each other and do a handshake between CAMG and MATLAB. And I am going to go directly and find the transfer function for F11, which is that I'm looking for. I directly go to the CAMGSYM file, and then I will go and say find. Please find F11 for me, and I'm going to define this as my output. Okay, so this is my output in here is this is defining the rows of the C and the D matrices, because while CAMG sets you up with all the outputs of the system, we need to activate the ones that we want. And so in this case, what we are going to do is we go and run the CAMG software. And here, what happened? Did I run or not? Yeah, there you go. So computer automatically derives the state space form for me in symbolic form. There is the C and the D matrix. There is only one. And then, of course, this is my transfer function, which is derived in symbolic form. And it has the, the couple of this, transfer function matrix. In this case, there's two of them. You can say, why is that? The reason is that in here, while this is my output, is relating to this input here and also to this input here. That's why I have two. Well, in this particular case, I'm interested on this because this input is going to be 0. So from that point of view, we could have suppressed this and have only one transfer function, but it doesn't matter. Right now we have two, and we have to take a look as to what MATLAB is telling us. It's telling us that, oh, hold on for a second, this was from a previous run. Where are we here? Right here, okay? In the inputs in here, it's telling you that the first input is SE1. So our transfer function in reality is in relationship to the first input, SF14 is the second one. We're not interested on the second one, we're interested on this one. We're interested on this transfer function, and the computer puts it like this when you have the denominator, as you can see, is a fourth order system, and it has the coefficients that make up each power of s in the denominator, this is very good for control systems to study the sensitivity analysis of the system. So we don't have any numbers, so I expect MATLAB to just stop there. But what I can do is, so up to now, we have obtained the transfer function of the system, and now we need to obtain the frequency response. But to do that, to get those body plots, we need to give some values to the physical parameters. Otherwise, how are we going to do this? So I think we need to go back over here and up here to give the values to this. So I'm just going to give them some nominal values that I have, that I would do something like this 2 and this 2, 3, and then this one C1 like 1 over 30, and 1 would be, let's say, like 10, and the other I, there's 2 I's, 2 and 10 would be good. These are, let's also put it as at level 3. This may be as 1 over 20 like this. Yeah, okay. Smaller. let's do it the reversing here. This would be 2, and then maybe we'll put this one up a little bit. Well, let's see what happens. So if I do this, and I give it some, the computer is going to replace these values, and the matrices, as you see, no longer are symbols, but they are numbers right now. They are calculated numbers. And you have 4 state variables right here, the positions of the springs and the momentums of the masses. But we ask for a transfer function for the velocity. So in this particular case, it will calculate the transfer functions and give me already the plots. So let me go back in here for a second in here. You see what it says? From input 1 to output 1, and from input 2 to output to the output that we have. And this is my transfer function right there. Okay, that's the one that we're working with. And automatically the computer has given me the body plot of the transfer function. Here's the magnitude plot, and this is the phase plot. This root locus plot, we're going to leave it for now, but let's just do the frequency response first, because that's what we're concentrating on right now. And also, so this is figure 2 is for the other one, and it will give us the the step input for both transfer functions, and it gives us also the impulse response for both transfer functions. So these are time domain responses. So what I was trying to say before is that automatically CAMG has done this response in the time domain using the transfer function, which is in the frequency domain. So that is the entire thing from beginning to end. So let's